In this video, we're going to look at the matrix representation of linear operators. Now let us designate a linear operator as f. That is basically a function that will be applied on any vector which might be given to you. Now let us say you have a vector space V, and this vector space contains a basis. Let's say one vector under it is written as E1, and another one is E2, and another one E3, and okay, let's just go on until we reach some amount of the vectors that will be within that vector space. If we took this operator and operated on these various vectors, we could actually form a new vector. So that means if I took this function and worked it on this, I would actually form a new vector. This representation is a new vector. Now, I could also have it to be in a second case where I have the vector operating on the second vector. Well, I have the operator operating on the second vector. I could also have the operator on the third vector continuously until you reach the last vector in that basis. Bear in mind, this is the basis. A basis is a sequence of linearly independent vectors within a vector space. So this will be the basis. And what we're trying to say is you could have this operator operating on this basis. Now, if you have this, you might be able to express any of those vectors as a linear combination of the others. So let us say I use this one. If I took out an operator and operated on the first vector, I would actually have it to be equal to the linear combination of the other ones, including this one. So you might be able to have something like this. So I might say this is A1, F, E1, and that will be plus E2, F, E2, and that continues until you reach AN, F, EN. So this is the basic idea behind the trick, I might say, or the principle that will lead us to the matrix representation of it. So just hold this introduction at the back. Now we're actually going to put more flesh to this explanation and create more meaning from it. So let us say you have a basis that is E1, E2, E3, until we have En, and all these, they belong to the vector space. And let us say we have an operator that is represented as an F. Now if we worked the operator on the first vector, we're actually going to have something like this. So I'm going to say A11 of FE1 plus A12 of FE2 plus let us just continue until we reach A1N of FEN. So what does this mean? In this case, we're trying to say that if you use the operator and operated on any vector within the basis of the vector space, you are going to get a new vector. Now that new vector is supposed to be a linear combination of all the other vectors, or all the vectors within that basis. So in this case, we're going to have the linear combination. Now if we wanted to write the linear combination of the form, you know that we need to take scalars and multiply it with the vectors. So in this case, you're going to have A11 and A12 until you reach A1N. So what we're trying to do here, we're trying to create a matrix form of this operation, this linear operation. The N, which you see here, that actually stands for whichever number of the last digit which might be within this expression. So you could have it as A14. I need to rewrite this. A14 You could also have it as A17. You could have it as A1R. Okay, so stuff could just continue going on, and we would be able to form many forms of it depending on the dimension of the basis of that vector space. Now, what if we took the operator and worked it on the second vector within that basis? So that is going to give us an A21 F E1 plus A22 of F E2, and you would still continue on until you reach 2n of F En. Now, how about if I took out the third? If I worked an operation on the third vector, that will give me something like this. That is going to be A31 multiplied by F E1. Now, we know we're trying to write the linear combination for each vector, which will be formed from the linear operation of the forms which are represented there. That is from the basis. So you could write it. This is going to be A32, and you're going to have F E2. And that also continues. And here you're going to have a 3n and an FEN, right? Now, if I went on and let's say I continued until, I'm going to use this, take it a little bit higher, okay? And I continued until I reached this. So that is En. That is the vector of the nth form. That is going to continue on these other side also. We could have an endless form of the linear combination of the answer. So here we're just going to have an n1, okay, and that will be multiplied by the new vector, which was formed as a result of the operation of the operator on that vector. In this case, it's going to be the nth vector. So you're going to have this, and here you're going to have n2 of FE2 continuously until you reach ANN of FEN, something like that. So basically that is what you're going to have. Now, if we had something like this, it's going to be very possible to create matrix forms of this representation. On this side, this is what we have. So I could well write this way. So this is going to be the operation of the operator on the first matrix. This is going to be the operation of the operator on the second matrix. And this here, we're going to have the operation of the third. That is the same operator, by the way, on the third vector. And the same operator operating on the fourth. So you're going to have something like this. This is on the right hand side. And on these other side, we're going to have something like this. So I'm going to have A11 and I'm going to have A12. And of course, we continue on until we reach A1n. I need to rewrite that. Now, over here, we're going to have A21, A22, continuously until you reach A2n. And to the last, or this one, I'm just going to write it as an A31. And then you have an A32 until you reach A3n. Now, what are we trying to write out? We are actually trying to write out the matrix form of the scalar coefficients of the vectors, which are actually going to be formed from the operation of the operator on each vector within the basis. So we know these are vectors. This stuff, which I underline, these are vectors. Now the coefficients which are in front of them, those are the ones which we want to use to create this matrix form. So I'm just going to wipe this first one away. So we're going to create another one. So let's say you have this. You could form something bigger. So I need to redo it. Yeah. Now remember, I said you could actually work this operation until you reach the nth form of the matrix given to you. So we should just write it this way, that you could reach an 1, and you're gonna have an an2, and here you're gonna have until an ann, and that is actually gonna be a matrix. You could actually form a matrix from this way. So I'm just gonna write this as a first. Remember, we had the first matrix, and then we had no, this should not be a matrix, this is a vector. So that is E1, and this is going to be E2. You're going to have E3, and that continues until you reach En. That is the nth vector. So I'm just going to create a dot here, and we're going to have an En right here. Now this form is actually the matrix form of the representation of the linear combinations of the operators. So we're going to have this. This is the column vector that represents the operators. So I'm just going to write it as an F. This actually stands for the coefficient matrix. This is a matrix that we have formed from the coefficients of the linear combination. So I'm just going to write that as, I should write that as an A. And then these ones are actually the coefficient of the vectors. So I'm just going to write that as an E. Okay. Now this particular form, this vector here, this is actually the most important thing from this equation. This is what we want to use to form the matrix representation of the linear combination of a linear operation. So this is what we're going to do. We have this stuff this way. So I need to rewrite it. This is going to be A11, and this is a A12, and here we have A1n. And then here we have A21. Here we're going to have a A31. And let us make this to be A22. And this is A32. And here we have an A2n. Here we have an A3n, like that. So this is the matrix representation. Now we could actually change this form into its transpose. Let us say this is a matrix form A. Now if we wanted to change this into its transpose, I'm just going to wipe this stuff out. So A transpose, that is going to be equal to A11, and here we're going to have an A21, and here we're going to have it up till we have an A1n. And for the second one, this row becomes a second column, so we should have an A21 and an A22, and here we're going to have it up till we reach A2n. So when we write that, then you're going to have the last row become the last column. So this is A31. Here you're going to have an A32, and you continue on until you reach an A3n. Now if you are actually able to form the transpose form of that matrix which was created, then you have actually represented the matrix form of it. This is actually very useful because you would use it to solve questions or answer questions which would require you to do that. So right now we're going to jump into questions involving it so that you would really understand what we're talking about. Okay, so here is a question we have. Let V be the vector space of polynomials in T. So T is actually the variable for the polynomial, and it's actually working over the set of real numbers of the degree that will be equal to or less than 3. And let D be a function or an operation. In this case, we're going to call D an operator, and it's actually operating on the vector space, which is actually mapping to the vector space. So that means if you have this particular operator work on the vector space, the answers you're going to have will create a set of a vector space. That is basically what that means. Now we know that this is supposed to be a differential operator, which is defined by this form. So if you have a d of this, there should be a d dt, and that will be p of t. So writing out a capital D here actually represents the first derivative of that function, or that vector in this case. Now we are required to compute the matrix of D and the basis, which is represented below. Now we know these bases actually contains 5 vectors. We have 1, we have t squared, so that is a t squared, we have t cubed, and there is a t to the 4th. So we need to work each one of them. Now we have D to be okay, we have actually said that we know that D is a differential operator. So let us start with the first vector within that basis, which is 1. So that is going to be D of 1. So D of 1 should basically be D dt of 1. This is going to give us 0. Now we need to express this 0 as a linear combination of the other forms. So that is going to be a 0, which will be multiplied by 1. And here we're going to have a 0t plus 0t squared plus a 0t to the 3rd plus a 0t to the 4th. Now let us try it for the second. That is t. So you got d dt, and this is with respect to t. So you need to differentiate t with respect to t. That is going to give us a 1. So in this case, we have a constant, and that will stay with the constant. So this is going to be a 1 multiplied by this. And we don't have no t's associated with this answer. So this pretty much is still going to be a 0t. We don't have no t squared, so that should be a 0. And we don't have no t cubed, so that is still going to be a 0. And we have a 0t to the 4th. Now let us try dt to the 2nd power, dt squared rather. So this is going to be dt. Now this is squared. If we differentiated t squared, that is going to give us 2t. So whilst this doesn't have anything no more, we have at least a 2t over here. There's no t squared, so that will be a 0t squared. And here we're going to have a 0t to the 3rd. This is going to be 0t to the 4th. So we have d dt raised to the power of 3. Well, so if we differentiated this with respect to t, that is going to give us a 2t squared. Now we know that this is the part that represents a constant, so there is 9 related here to that, so that would still be 0 multiplied by 1. Then you have a t raised to the power of 1, which doesn't reflect here, so that will be a 0t, and here we have a 3t squared, so that will take that position. And then we don't have a 3t up to the cube, so we're just going to say this is a 0t raised to the power of 3. And then we also have a 0t to the 4th. Now the last one is going to be dt to the 4th. So we need to differentiate t to the 4th with respect to t. So this is d dt t to the 4th. This is going to give us a 4t raised to the power of 3. Here we're going to have a 0, 1. And we're going to have a 0t. We're going to have a 0t squared. We're going to have a 0t to the 3rd. And finally, we're going to have a 4t to the 3rd. Now, looking at this, we can actually create our matrix form. this part actually stands for the column matrix of the operator. You could well use this one or this one, and that is going to stand for the right hand side. Now we know that we must create the right, well, this is actually the left, and that is going to be the column vector for the left, and this will be the column vector for the right. So how can we create the matrix for it? How's it going to look? So this is what we need to do. We need to clear these out. We know that for this form, which is the first line, we don't have none. All these coefficients, they're all zeros. Remember from the beginning part of this video, we talked about the fact that you need to create a matrix of the coefficients of those functions, no, not the functions but the vectors. So we don't have no coefficients here. That is practically zeros. So we're just going to write 0 for the first step. And this is 1, 2, 3, 4, and 5. So that is what we're going to have there. That is zeros in 5 places. Now we know this is actually the derivative of the first step. So I'm just going to wipe these out. I'll wipe this one out. And then for this one, we have a 1. We have a 0, 0, 0. So I'm going to write that out. This is a 1 and this is a 0, 0, 0, 0. And so this is going to go. And to this one, we don't have nothing here. We have a 2t. So this is going to be a 0. This is going to be a 2. That will be the coefficient of t. And here we have a 0, 0, and a 0. So I'm going to wipe these out also. And now to this one, we have a 0 here. We have a 0 here and a 3. So that is going to be a 0, 0, and a 3, and a 0, and a 0. So I'm going to take these out also. And we have the last one. A 0, 0 here, a 0, a 0, and a 4. So that is going to be a 0, 0, 0, and a 4 with a 0. Okay. So that is actually going to be the right-hand side matrix for the coefficients of the vectors which were actually represented. So I'm actually going to write them this way. This is 0, 0, 0, 0, 0. And we have a 1, 0, 0. I think I need to take it a bit higher. So this is 0, 0, 0, 0, 0. This is a 1, 0, 0, 0, 0. Then we have a 0, 2, 0, 0, 0. And then we have a 0, 0, 3, 0, 0. And then we have a 0, 0, 0, 4, 0. So that is what we have for the coefficient matrix. But you must bear at the back that we also have the column matrix or the column vector for the functions. So I'm just going to wipe these out and create that on this other side. So this is going to be what you have. I need to rewrite this. So this will be d1, and this is going to be dt. Here we're going to have a dt squared. And here we're going to have a dt raised to the power of 3. And here we're going to have a dt to the 4th. So that is a column matrix or the column vector for the functions or the operators. Now we need to multiply this with 1, t, basically this vectors within the basis. So that will be t squared. This is going to be t to the 3rd. And we're going to have a t to the 4th. So I'm really having some problems writing over there. So I'm just going to take stuff up. So I think I'm going to rewrite this. So here we have a 1 and a t squared, t to the third, t to the fourth. So here this is a 0, 0, 0, 0, and a 0. Then you have a 1, 0, 0, 0, 0, have a 0, 2, 0, 0, and a 0, have a 0, 0. I think I'm going to take it a little bit down. This is a 3 and a 0. And here you have a 0, 0, 0, and a 4 and a 0. So this is actually going to be the matrix form that you would have. Now we need to compute the matrix of D. So this basically is the greatest thing that we're trying to look for. But in order to get the final stuff, you need to find the transpose of this form. But this is going to be the main equation. So this is F, and this is equal to the matrix form multiplied by the entry form, or the vectors which are present within of that matrix form. This is exactly what you're looking for. Now, what is going to be the A transpose? How's it going to look? So I'm just going to wipe this and write it out. So that will be a 0, 0, 0, 0, and a 0. We're going to have a 1, 0, 0, 0, and a 0. We would have a 0, 2, 0, 0, and a 0. We would have a 0, 0, and a 3, and a 0, and a 0. We would have a 0, 0, 0, and a 4, and a 0. So this is A transpose. And this is exactly what we're looking for. D of, in this case, we're using T, so that will be sub T. This will be the answer to the stuff.